Quantum computers are supposed to change everything: drug discovery, climate modeling, breaking encryption, designing materials that don't exist yet. That is the promise that has been dangled in front of scientists and investors for decades. And for most of that time, quantum computers have been powerful in theory and nearly useless in practice. But in 2025 and 2026, one company quietly repositioned itself to become the reason quantum computing finally stops being a future promise and starts becoming a present reality. That company is NVIDIA. And what they just announced might be the most important pivot in computing since the invention of the GPU. To understand why this matters so much, you first need to understand the single biggest problem with quantum computers. It is not that they are slow. It is not that they are expensive. The deepest, most fundamental problem with quantum computers is noise. A quantum computer processes information using qubits, quantum bits. Unlike the regular bits in your laptop, which are either a 0 or a 1, qubits can exist in a superposition of both states at the same time. That is what gives quantum computers their extraordinary theoretical power. But qubits are also extraordinarily fragile. They are so sensitive to their environment that even tiny vibrations, temperature changes, or electromagnetic interference can cause them to flip, decay, or produce wrong results. This is called quantum noise. And right now, even the best quantum processors in the world make an error roughly once in every 1,000 operations. That sounds okay on its own, but to run a useful real-world application, to actually simulate a drug molecule, to break an encryption algorithm, to model a climate system with real precision, that error rate needs to drop to roughly 1 error in every trillion operations. The gap between where quantum computers are today and where they need to be is not small, it is enormous. And it has been the wall that has stopped quantum computing from leaving the lab and entering the real world for years. NVIDIA's answer to that wall has a name: Ising. In April 2026, NVIDIA launched what it called the world's first family of open source AI models, specifically designed to solve the quantum noise problem. The Ising model family is built around 2 core functions. The first is quantum calibration. Before a quantum processor can even begin running a computation, it needs to be tuned. The physical control signals, things like microwave pulses and laser frequencies, that manipulate qubits have to be adjusted to account for hardware imperfections, temperature variations, and drift over time. This process is called calibration, and it has historically taken days of painstaking manual work from teams of physicists. Ising calibration is a 35 billion parameter AI model that reads measurement data coming directly out of a quantum processor and figures out on its own how to adjust those control signals. It reduces the calibration process from days to hours. That alone changes the operational economics of running a quantum computer in a fundamental way. Labs and companies that used to spend the majority of their time just getting a quantum processor tuned and ready can now spend that time running actual experiments. The second function is quantum error correction decoding. Even after calibration, qubits still make errors during computation. Quantum error correction is the technique of encoding logical information across multiple physical qubits so that errors in individual qubits can be detected and corrected without disturbing the computation. But here is the catch. Error correction generates enormous amounts of data. A quantum processor running error correction produces terabytes of qubit measurement data every second. And all of that data needs to be processed by a classical computer in real time, faster than new errors accumulate, in order for the error correction to actually work. This is called decoding. It is computationally brutal, and it has been another hard ceiling on how far quantum computing could scale: NVIDIA's Ising. Decoding models are 3D convolutional neural networks trained to handle this process faster and more accurately than any previous approach. They deliver up to 2.5 times faster decoding performance and 3 times higher accuracy than traditional methods. NVIDIA demonstrated these models at code distances up to 31, a technical metric tied to how well a system can suppress errors. That corresponds to the regime where hundreds to thousands of physical qubits work together to represent a single reliable logical qubit. That is the scale that current quantum computing roadmaps are targeting. Ising is not a research toy. It is a production tool for the frontier of the field. Jensen Huang, NVIDIA's CEO, described Ising in terms that cut to the core of what the company is actually doing here. He said that with Ising, AI becomes the control plane, the operating system, of quantum machines, transforming fragile qubits into scalable and reliable quantum GPU systems. That phrase, the control plane of quantum machines, is the key to understanding NVIDIA's entire strategy. They are not trying to build their own quantum processor. They are not competing with companies like IBM, Google, IonQ, or Quantinuum on the hardware side of quantum computing. What they are doing is far more strategic. They are positioning AI, specifically their AI, as the indispensable layer that every quantum computer in the world needs to function. The GPU runs the AI runs the quantum computer. NVIDIA sits between the quantum hardware and every application it ever runs. If you are enjoying this breakdown, hit that like and subscribe. More deep dives on the technologies reshaping the future are coming every week. To make that vision physically real, NVIDIA also developed something called NVQLink. Think of NVQLink as the physical and software bridge between NVIDIA's GPU supercomputers and quantum processors. It is an open system architecture that couples a GPU-accelerated server directly to a quantum processing unit with a data throughput of 400 gigabits per second and a latency of less than 4 microseconds. To put that in perspective, 4 microseconds is fast enough to run error correction algorithms in real time, which is precisely the latency requirement for quantum error correction to actually work at scale. The system delivers 40 petaflops of AI performance, that is 40 quadrillion AI operations per second, available to support and control the quantum hardware in real time. NVQLink is not a one-off experiment. At its launch in late 2025, NVIDIA announced that 17 quantum hardware builders, 5 quantum control system builders, and 9 of the United States' most prestigious national laboratories had already committed to integrating with it. That list includes Brookhaven National Laboratory, Fermilab, Lawrence Berkeley National Laboratory, Los Alamos National Laboratory, MIT Lincoln Laboratory, Oak Ridge National Laboratory, Pacific Northwest National Laboratory, and Sandia National Laboratories. By November 2025, world-leading supercomputing centers across Asia, Europe, Australia, and the Middle East had also adopted NVQLink. These are not future partners or letters of intent. These are institutions actively building quantum GPU hybrid systems using NVIDIA's platform right now. The software layer that ties all of this together is called CUDA-Q. For anyone familiar with computing history, the name carries enormous weight. CUDA was the software platform NVIDIA developed in 2006 to let developers write programs that run on GPUs. It was the single most important reason AI took off the way it did. Every major AI trained on systems running CUDA. NVIDIA essentially became the operating system of Move applied to quantum computing. It lets researchers and developers write hybrid programs that seamlessly draw on classical CPUs, NVIDIA GPUs, and quantum processor they might want to run on. CUDA-Q abstracts that complexity away even further. Research institutions immediately started publishing serious results. The University of Edinburgh reported a 900-fold speedup in quantum error correction. Sinica and Kipu Quantum ran a 43-qubit quantum simulation across 2,048 NVIDIA GPUs. University College London, the Technical University of Munich, and IQM all published GPU-accelerated biomolecular research using quantum classical hybrid. What makes this moment worth paying attention to beyond the technical details is computing was essentially a single story. Transistors got smaller, chips got faster, classical computers improved on a predictable curve. Quantum computing has always represented a potential discontinuity, a completely different model of chemical interactions, which is central to drug discovery and materials science. They include optimization problems at scales that classical computers cannot handle, which matters for logistics, finance, and energy grids. They include cryptographic applications, which is why every government security agency in the intermediate scale quantum. A phase where processors are powerful enough to be interesting, but too error-prone to be practically useful. What NVIDIA is doing is building the infrastructure that gets quantum out of the NISQ era without requiring quantum hardware to solve the noise problem. It provides the computational muscle to do all of that in real time. The real-world implications are already materializing. Quantinuum, one of the leading quantum hardware companies, used NVIDIA's CUDA-Q platform in collaboration with a pharmaceutical company to achieve a 234-hour relevant to pharmaceutical development. That is a direct, measurable example of quantum chemistry workflow for drug development that ran on IonQ quantum processors and NVIDIA GPUs simultaneously. These are not theoretical future applications. They are happening now using the infrastructure NVIDIA is building. And as the error rates improve and the qubit count scale, the same workflows that currently deliver incremental improvements will start delivering breakthrough results. To fully appreciate the strategic position NVIDIA has built, consider the analogy of the AI era itself. When AI started becoming powerful, in the early 2010s, there were many AI research groups, many different neural network architectures, and many different software frameworks competing to become the standard. NVIDIA did not compete in any of those spaces directly. They sold GPUs, they maintained CUDA, And they made sure that every researcher, every startup, and every lab doing serious AI work depended on NVIDIA hardware and NVIDIA software to do it. By the time the world understood what AI had become, NVIDIA was already the unavoidable foundation underneath it. They superconducting qubits, trapped ions, neutral atoms, photonic systems, silicon spin qubits. NVIDIA is not betting on which one wins. They are building the AI control layer and the software integration platform that every one of those approaches needs to function at scale. Whoever wins the qubit race, they will need NVIDIA's stack to make their hardware useful. That is not a speculation. That is the explicit architecture of NVQLink, which was deliberately designed to be hardware agnostic and open, supporting all of the major quantum hardware approaches simultaneously. NVIDIA has also built a physical facility to anchor this strategy. The NVIDIA Accelerated Quantum Computing Research Center, which the company calls the NVAQC, is where partner quantum hardware is directly integrated with NVIDIA GB200 NVL72 supercomputing systems, the most powerful hardware ever deployed for quantum computing applications. The facility and commercial partners together under one roof to work on the hardest remaining problems in quantum error correction, qubit. The global quantum market reached $1.9 billion in 2025 and is projected to grow at 30% annually, reaching $3 billion by 2028. Those numbers will look modest in hindsight if the technical breakthroughs being pursued right now materialize on schedule. Ecosystem, building on CUDA-Q, running on NVQLink, using Ising for error correction, are going to have years of accumulated experience and optimized workflows before anyone starting from scratch. Make sure you subscribe and leave a like if this kind of content is useful to you. Understanding what is actually happening at the frontier of technology is more important now than it has ever been. Developed by physicist Ernst Ising in the early 20th century to describe how interacting particles influence one another in magnetic systems. It became one of the most widely complex systems, naming their quantum AI model family after it is not just branding. It is a statement about what NVIDIA believes they are building, not a specialized tool for a category of computing develops. The same way the original Ising model simplified the understanding of complex physical systems, NVIDIA's Ising is designed to simplify what we are watching unfold in 2026 is the early stage of a platform war, not between GPU companies, not between AI labs, between entirely different models of what the next generation of computing looks like. Quantum hardware companies are building the processors. Classical supercomputer makers are building the infrastructure. And NVIDIA is positioning itself as the indispensable connector between all of them. The company whose software you need, whose hardware you plug into, and whose AI models run the control plane that makes quantum computers function at all. If that sounds familiar, it should. It is the same story that played out with AI and GPUs over the past decade. And if NVIDIA executes on this strategy the way they executed on that one, then the announcement of Ising and NVQLink in 2025 and 2026 will look, in retrospect, like the moment the quantum computing era actually began. There's a dimension to this story that deserves its own attention, and it is about who controls the future of computing power at the national and geopolitical level. Quantum computing is not just a technology story. It is a security story. It is a sovereignty story. The encryption systems that protect everything, banking, military, communications, government infrastructure, private data, are based on mathematical problems that classical computers cannot solve in any reasonable time frame. Quantum computers, at sufficient scale, could break those encryption systems. That is not a distant theoretical concern. It is the reason the United States National Security Agency, GCHQ in the United Kingdom, and intelligence agencies around the world have been funding quantum research for decades. They are pushing hard for post-quantum cryptographic standards right now, before the machines exist that could exploit the vulnerability. Every month that passes without a fault-tolerant quantum computer is a month that sensitive encrypted data can be harvested and stored, waiting for the day when a quantum computer capable of cracking it finally exists. This practice is sometimes called harvest now, decrypt later, and it is actively happening. The race to fault-tolerant quantum computing is not just about who gets to make better drugs or more efficient batteries. It is about who gets to read everyone else's secrets. In that context, NVIDIA's decision to make NVQLink an open architecture deliberately, supporting all quantum hardware approaches, sharing the tools widely with national laboratories and academic institutions, carries geopolitical significance. The United States and its allies are effectively trying to build a quantum ecosystem that is faster, more capable, and more integrated than anything being developed by rival nations. NVIDIA, by becoming the connective tissue of that ecosystem, is not just making a business decision. They are, intentionally or not, helping to determine what the Western technological frontier looks like in the most sensitive area of computing. China has invested aggressively in quantum research and has claimed several milestones in quantum communication and quantum processor development. The competition is real, and it is intensifying. The fact that 9 U.S. national laboratories, including Los Alamos, Sandia, and Oak Ridge, institutions that collectively represent the core of American scientific and defense computing, have committed to building on NVIDIA's quantum AI integration platform is not a coincidence. It is a strategic alignment. For developers and engineers watching this space, the near-term practical question is what Q2Q means for them. The honest answer is that right now, the number of people writing hybrid quantum classical applications is small, quantum hardware is still expensive, access is still limited, and the programming models are still unfamiliar. But that is exactly what CUDA was like in 2007. The developers who learned CUDA early, who built libraries and tools and workflows on top of it, became the people who built the AI revolution. The analogy is not perfect, it never is, but the structural pattern is similar. An NVIDIA-backed platform with open source tools, broad hardware support, and aggressive institutional adoption is being positioned as the standard before the market is fully formed. The developers who invest time in Q2Q now are going to be extremely valuable in 5 years when the applications start materializing at scale. The quantum computing industry reached $1 trillion in projected long-term market value estimates precisely because the applications it unlocks are not incremental. If you can simulate a molecule exactly, not approximately, not with classical shortcuts, but exactly the way quantum physics actually governs it, you can design drugs that target diseases at the molecular level with precision that current methods cannot achieve. You can design battery chemistries that store more energy than anything available today. You can design superconducting materials that transmit electricity without loss. These are not marginal improvements on existing products. They are category changes. And the AI quantum hybrid approach NVIDIA is building is the first credible, technically grounded, industrially supported path toward unlocking them on a timeline that matters in this decade rather than the next one. The calibration tools are working. The error correction decoders are deployed. The supercomputing labs are online. The hardware builders are integrated. The software platform is public. The research center is running. The pieces are in place in a way they have never been before. What NVIDIA has done by launching Icing and NVQLink is not just release a product. They have made a bet on what computing looks like in 2030 and beyond. They have backed that bet with the full weight of their hardware ecosystem, their software platform, their research infrastructure, and their relationships with the most important scientific institutions in the world. They are saying, as clearly as a company can say it, that the future of computing is not classical computers getting faster. It is not quantum computers working alone. It is AI supercomputers and quantum processors working together, with AI serving as the intelligent control layer that makes quantum hardware reliable enough to be useful. And they are saying that NVIDIA will be the company that makes that connection. The GPU made AI possible. Now NVIDIA wants AI to make quantum computing possible. That is the loop they are closing. And if they succeed, the implications for science, medicine, security, and technology will be greater than anything the GPU revolution produced. This is the most important computing story of 2026, and it is only just beginning.